Today I want to start off with a bunch of do's and don'ts for solving logarithmic equations. I know it looks really texty here and a lot of reading, just bear with me. So do, of course, follow BEDMAS. We still have to follow the order of operations. And then the don't on that, I couldn't think anything good to put there, so I just put don't not follow BEDMAS. Do distribute into brackets with coefficients and variables. You know you can distribute that. The negative 5x squared comes in with multiplication, no problem. But don't distribute into brackets with the word log or sine or a single exponent. So for example, log x plus 1, you don't distribute the word log in, that's wrong. You don't distribute the word sine in, that's wrong. And when you just have a power of 2, you don't just distribute the 2 into it and get 2x squared minus 3 squared. That's wrong. So that's improper use of, it's really BEDMAS, but it's also improper use of distribution. Do use the quotient law, of course, lovely. We've proven this, you know this law. And don't confuse it with dividing two separate logs. It's almost like you're distributing log to the numerator and denominator. So this is not, see the not equal sign there? These are not the same. I can't take the log base A and distribute it to the x and distribute it to the y. That's not how this works. And we have proven this law, and you can go back and look it up, or actually it was in your textbook. So this, make sure you don't mess up the law of logs and you write it the wrong way. These two are not the same. Again, with the product law, same idea. Oh, that A there should be a subscript, sorry, that should be a base. When you have the same bases and you're adding logs, you can multiply the inputs together. But don't try to attempt to create your own adding logs law by doing something, taking this, which is fine, but then turning it like factoring out the A, factoring out the log A. So that's not correct. So make sure you follow this law. Also, do consider like terms. What are like terms? 5 log x plus 4 log x is 9 log x. They have the same base 10, invisible 10, so we can add them together. And so you can, when you get to this question here, you can look that up. But don't add unlike terms. So 5 log, again, that should be a base, sorry, subscript 2 there. And this should be a subscript. I think something happened when I transferred it to PowerPoint that I lost those. So that should be a subscript 2. If you don't have the same base, this is a base 2, this is a base 10, we can't add them together, or a base 1 even, right? You can't add them together if the bases aren't the same. And there's a base 2 and a base 3, that doesn't give you a base 5. So they have to match, they have to have the same log and base. Do remember the domain of logs. Whatever your base is, if you have a 0 here, that's undefined. You can picture the graph and maybe that will help you to make more sense, or take a look at the graph. Same thing with the negative input, that's also undefined. And don't forget the domain of logs. So if you have log base x of 16 equals 2, that means in exponential form x squared equals 16. So our x could be a 4, but not a negative 4, because remember that x was originally a base of a log. If it didn't start with this line, if you cross this line out, you just started a question here, for sure you could have positive 4 and negative 4, but because x originally came from a log, we have domain restrictions on logs. So those are a bunch of do's and don'ts about logarithmic functions. Example 1, solve the following logarithmic equations. Okay, what should we do first? Take a look at A. What should we do? So we have a log on one side and a constant on the other. This one's similar, this one's 2 logs. What do we do with this one here? Well, we're going to convert it to exponential form. So we start with the base. So the base becomes the base of an exponent. So that's going to be 4 to the power of 2 equals x plus 3. And now we could solve this probably in grade 8. That gives us 16 equals x plus 3. X is 13. That was pretty straightforward. Same step, apply it here. This one's a little different because I don't see a base there. So you have to remember what it means when there is no base showing. What's the default? It's a base of 10. So 10 to the power of 5 equals x, and that just is a 1 with 5 zeros, right? That's what the power of 5 is, so 100,000. Next one. Now this one, it doesn't really make sense to convert this to exponential. We're going to get this coefficient 3 and move it up. Because we have logs, we're allowed to do that. But still, converting to exponential form isn't a great strategy when we have logs on both sides. So we're not going to convert to exponential. So can you think of anything else here? Well, let's go over kind of a basic premise. If you have log base a of m equals log base a of n, then m equals n, because this part here is exactly the same as this part here. So whatever m is, it's got to be the same as n. If m is 2, then that's got to be the same. If we know that they're equal, we know they're equal. So looking up at the question that we have here, the log and the base here are exactly the same. It's invisible base of 10, log invisible base of 10. That means x must equal 7 to the power of 3, and that's 343. Okay, so those are that's the first example. Pretty straightforward questions, but just a few little things I wanted to point out before we got into some more complicated stuff. Example 2. Solve and check. Well, question says check. If it says check, we have to check. Log base 9. Okay, I'm not going to read all that out. So what should we do first here? Well, we're going to do the product law first so that we can rewrite with a single logarithm. So we've got a log base 9, log base 9. That should always be a little light bulb that goes off over your head. Oh, look, log base 9, log base 9. My bases are the same. I'm adding. Go back to your do's and don'ts. Make sure you set this next step up correctly. With the product law, we've got two log bases that are the same. What do? We can put them together like this. I put them together with a square bracket, but we're multiplying these inputs together here. 1 log base 9, and these two come together with multiplication. So now we're just going to use FOIL or distributive property or binomial expansion. We're going to multiply all that stuff together. Collect like terms. When we do that, in the bracket, we have x squared minus 2x minus 15. So this is good here now because we had 2 terms here equal to 1 term on this side. Now we've all got it together as 1. Now it's actually back to what our example 1 question looked like. We have a log base with 1 big input. This is 1 input. It's all together with a bracket. It's equal to 1. So for my next step, I can convert to exponential form now. The base is what? What's the base? It's a 9. 9 to the power of 1 equals this. That's my next line. Again, now this is like a grade 10 question. So 9 to the power of 1, of course, is 9. We bring it over, and now we have a trinomial. We have a trinomial, and the first thing we do with a trinomial, if we can quickly factor it, we would factor it. If we can't, we would go to the quadratic formula. So just take a minute and think, okay, is there anything that multiplies to negative 24? 2 numbers that multiply together to give me a negative 24. And those same 2 numbers add or subtract to negative 2. So we're doing a sum and product here. And yes, there is. It factors to x minus 6 and x plus 4. So that gives us 2 answers. It gives us 1 root here when x is 6. So when x is 6, we put in a 6 here. I don't care. This will be 6 plus 4. This will be a 10. But 0 times anything is 0. So that's one answer. X could be 6 or x could be negative 4. Either of those answers will give us a solution of 0. But we are not done because the question said you have to check. So we have to check the validity of the answers when we have logs for a reason here. Let's first check x equals 6. I'm going to check that over here. So here's my original question broken up into a left side, right side. When you check, you always have to do that, or you could draw a T-chart if you prefer. You could do a T-chart, like just draw a vertical line here and then a horizontal line here to separate them. The important part is you're separating the left side from the right side. You always check in the original equation, never down here, because if I made a mistake and I check into my mistake, I won't catch it. So I want to check down here. I'm going to put in wherever I have an x, I'm going to put a 6. There we go. Now we just take care of those little brackets. We get log base 9 of 1 plus log base 9 of 9. Now, some of us, I really hope we're getting to a stage where we can get the answer for each piece. So right here, log base 9 of 1. Can you do that without having to work it out? If not, you just work it out. So I would, if I need to, I'm going to write log base 9 of 1 equals, and I'm going to pick a. So that gives me 9 to the power of a equals 1. 9 to the power of what is 1? So in this case, a would be a 0. So I'm going to get a 0 here equals, this one's 0, plus, next one, same thing. If you want to, if you can see the answer right now, then you write it down. But if not, we're taking log base 9 of 9, making it equal to maybe this time a w. 9 to the power of w equals 9. What is w in this case? It's a 1. So we get 1. And that's the same as our right side. Therefore, left side equals right side. So what? Why did we do that? Therefore, x equals 6 is a solution. That's what we just proved, because we got the left side to equal the right side. We don't need these numbers here to equal 6. We need them to balance and equal each other. Let's try our next one. We're going to check x equals -4. Again, I go up to my original question, and you could turn it into a table here if you want. Whoa, oh, shouldn't draw through that. You can turn it into a table if you want, and you can rewrite it though. Always rewrite it. And then you can sub in for your x here, separating your left side from your right side. So there is the question written down. Now I'm going to sub in for those x's, and I just went ahead and skipped ahead and did the math. Now, again, can we do this in our heads? This one would be, let's say we're making that equal to b. That would be 9 to the power of b equals -9. Well, what's that? 9 to the power of b equals -9. Are you thinking about maybe -1? Is 9 to the power of -1 equal to -9? No, because 9 to the power of -1 is 1 over 9. So that's not right. So actually what's happened here is we are not getting a root. We are not getting a solution on this part here. It's like when you find looking for the square root of a negative number. There's no solution here. This one is inadmissible. So I don't really need to continue on. I know that the -4 is not going to work, but let's just, for fun, let's just check this piece here. I already know that the -4 didn't work on one side, so it doesn't matter if it works on this side or not. But let's just check it. That, if I made that equal to, what haven't I used yet? I haven't used a e. Okay. Base 9 to the power of e. I shouldn't use e. That's a special, oh, that's a special number. Okay. F equals -1. Okay. What exponent could be here? What exponent? What about 0? 9 to the power of 0? Is that -1? No, that's 1. Again, we don't have an answer. This one's also inadmissible. There's no solution here. So x equals -4 is not a solution. The only solution we have is, oops, x, I messed that up, fix that. The only solution we have is x equals 6. And in a way, this is a bad example because it happened to work out that the negative number didn't work and the positive number did work. That doesn't have anything to do with it. It's because this, when I subbed in, turned out to be negative. So even if I would have subbed in a 2 here, which is a positive, if I would have subbed in a 2, that still would have given me an inadmissible answer there. So it's not because one is positive and one is negative. Don't think that. It's because after we subbed it in, we couldn't find a value. Nothing works. So that one is inadmissible. So the only solution for this answer is x equals 6. So if the question says check, you've got to check, and then you should get in the habit of checking these questions anyways when you get 2 answers. Just do a quick check, Remember, the logarithm of a negative number is undefined. So if you get a negative number, that's going to be an inadmissible root. Oops, I wrote that there, but you can't see it. Let me just erase this here. There. The logarithm of a negative number is undefined. So let's get some applications of this and do a few word problems. Example 3. This is a common use of logs as the decibel scale. Hopefully you've heard of what decibels are before. Decibel, lower d, capital B, is a logarithmic scale. It measures sound levels. The threshold of pain for the human ear is about 120 decibels. That's when you start feeling the pain of too loud, of the sound being too loud. Normal conversation is about 50 decibels. A jet takeoff is about 140 decibels. Damage can occur to the human ear with sound levels that are greater than or equal to 85 decibels. So this is, you're going to damage your ear before you feel any pain. So if you're reading this thinking, oh, my ear has never hurt from sound, that doesn't mean you haven't damaged your hearing. So this is your, at this level where you can get damage occurring. Martin's at a rock concert and it has an intensity of 80 watts per square meter. Watts per square meter. Is Martin at risk of hearing damage? That's a whole different unit. We were talking about decibels a second ago, and now we're talking about watts per square meter. By the way, the decibel is 1/10 of a bell. That's the deca part of it, which is named after Alexander Graham Bell. So we have an equation. You don't have to memorize it. I will give you this equation, and I is intensity. I naught. This is an interesting one here. I naught is 10 to the power of negative 12 watts per square meter. That's what minimum intensity detectable by the human ear. So that's always going to go in. That's your constant. Remember we did the earthquake question and we're comparing one earthquake to another earthquake? Well, for intensity, for what we can hear, it's always this number. That's not going to change. So that number is always going to go in down there. So we're trying to figure out if Martin has suffered any hearing damage. So where do you think this number is going to go? Where would that 80 go in this equation? Now it's an intensity number, so it's got to go in for one of these I values here. Now we already know one of them is I naught, so the 80 is going to go in, sub in for I. L equals 10 times log, now the I in the numerator is 80, and the denominator is 10 to the power of negative 12. That is all calculator work. So you got to get your calculator right now. The steps, it depends on how your calculator works, but make sure you don't just do log of 80 and then divide that by 10 to the power of negative 12. You're finding log of this piece right here. So you might need to, on my calculator, I would have to figure out that number first and then find log of it so that it wouldn't just find log of 80. So I want you to try that. I will tell you the right answer so you'll know if your calculator is working or not. Log equals approximately 100, or L equals, sorry, 139.03. So always with word problems, I need a sentence for you to prove to me that you're not just punching numbers into a calculator. You actually know what you found here. What did you find? What did you find out about Martin? So what we have here, this number, this L number is the level of the sound level, right? The sound level is 139 decibels. So if his sound level is 139 decibels, is he at risk of hearing damage? So the sound level is 139 decibels, which means Martin, what? Absolutely, he is at risk of hearing damage. 85 decibels is going to put him at risk of hearing damage. 120 is pain for the human ear. So hopefully Martin's standing way back from the speakers and he is maybe wearing some ear protection. So Martin, take care of your ears. Next question. Last question, I think. Yeah. Example 4. Jessica and her team of botanists discovered that the number of plant species, S, contained in a patch of lawn with an area A square meters is modeled by this equation. So Jessica and her team came up with this equation. Of course, A has got to be greater than 1. Use Jessica's formula to estimate the area of the lawn that contains 20 plant species. 20 plant species, okay. So we've got her formula here, this formula, and we've got a new number, 20. Where's the 20 going to go? The only unknowns we have are an S or an A. Which one is it? S or A? It's S, so, which is good because I hate using S. It looks like a 5, so I'm glad I'm replacing that. 20 equals 10.7 times log of capital A plus 8.1. So now we've got an equation to solve. We're going to subtract 8.1 from both sides. Subtract 8.1. Then after we do that, we're going to divide everything by 10.7. Divide everything by 10.7. So then what we'll have is log A will be isolated. So when I do that, I'm getting about 1.112 equals approximately, so we've got rid of these subtracted and then we divided these, is log A. Now do you remember what I told you when you have on one side a log and on the other side a constant? Yes, I know you remember. It was just 5 minutes ago. We're going to convert it to exponential form. So converting to exponential form, what's my base? That's an invisible base there of a 10. It gets the exponent of 1.112, and that's equal to, my input there's A nicely isolated. So you get out your calculator and you get an answer of approximately 12.946. And what does that mean? What did you just find? Did you just find that she can get about 13 species of plants in her nice lawn here? What did you just find? What's your sentence going to be? We've got to finish this. We know that we've got a patch of lawn that contains 20 plant species. What about that patch of lawn that contains 20 plant species? What is this? What's that number? Finish the sentence. It has an approximate area of 13 meters squared. So that's what Jessica and her team of botanists have figured out with their formula. That's the end of this lesson, and that was a 23-minute lesson, so that's pretty good. We've had definitely some longer ones this unit. So remember to let me know if you have any questions and do lots of practice.